Good day, students. Welcome to math.serve.com. In this clip, we're going to be going over question number 6 on the Unit 4 test on the application of derivatives. In this example, we're going to be going over an optimization problem that involves a rectangle inscribed in a parabola. Okay? All right. Let's take a look at the question. It says a rectangle has two of its vertices on the x-axis and the other two above the x-axis on the parabola y equals 12 minus x squared. So we are to find the dimensions of the rectangle with the maximum area. So in this problem, we are optimizing area, okay? Before we get started, let's go over the steps for solving optimization problems, okay? So step number 1, you want to model the situation by using a well-labeled diagram. You can then use your diagram to create a primary function and a constraint function or functions. And then step number 2, you want to substitute the constraint function into the optimization function, and then you will state your domain on the constraint on the independent variable. And then part 3, you want to find your extremas. Okay, your potential extremas are a combination of your critical points and your endpoints if the interval is closed. Step 4, you classify the extrema, and then lastly state the meaning of your result. Alright, so I'm going to be applying the procedures here to this problem. You can see a little guide I have on the right. So first thing we're going to do is create a model or diagram. We have a rectangle inscribed under a parabola, so what does that look like? So first thing to do, let's go ahead and sketch our parabola. It's a rough sketch, so we are modeling right now. We're in step 1, which is to model. If you look at this equation right here, it's a parabola that has been reflected downwards and shifted up 12 units. Okay, so we can put this as 12, and then it goes down something like this, and then in the other way like that. Okay, this is just a rough sketch. And then we have a rectangle that's inscribed in this parabola right here. So let's go ahead and sketch a rectangle inside the parabola. Okay. All right, so we are trying to maximize the area of that rectangle. That's the goal of this problem. All right, so let's see what we have. So we need to find the dimensions of this rectangle. Okay, so let's see. We can call this x. All right, x by x. So the width of our rectangle is going to be 2x units long. Okay, so how wide is our rectangle is going to be 2x units long. So width is 2x. And then how high is it? What's the height? Well, if we look at the coordinates of this point right here, the coordinates of any point on the parabola is given by x comma y, which is 12 minus x squared. So the y coordinate represents the height of our inscribed rectangle. Okay, so if we go like this, from here to here, that's our height, and it's given by 12 minus x squared. Okay, all right, so let's go ahead and write down our primary function. The primary function is the area, which is length times width. Okay, and then our constraint for secondary functions are the length. The length is constrained by uh, well, we're doing width times height, so we can also call this the length, it doesn't matter. So the length is 12 minus x squared, and then our width, how wide is it? 2x. Okay, now what's the next part? Part 2, we're going to make a substitution. We want to create a function in just one variable that we can use to find the extrema. Okay, so step 2, we're going to be substituting. So let's see. Do you see the substitution we can make here? We just substitute 12x squared for the length and 2x for the width. And then that gives us an area as a function of x. Okay, so the area as a function of x is 2x times 12 minus x squared. What are the constraints on my domain? How small can x get? X can get as small as 0. Okay, and then how big can x get? The maximum value x can attain is the x-intercept of the parabola 12 minus x squared. All right, so to find the x-intercept, we'll simply set 12 minus x squared equal to 0, and then we'll have x squared equals 12, and then if you get x by itself, you will have plus or minus square root of 12, which is 2 root 3. All right, so the maximum value that x can attain is 2 root 3. Okay, all right, so there goes the domain of our on the independent variable. All right, now we're going to proceed to step 3. We're going to find the potential extremas. Okay, we already have two potential extremas, the endpoints 0 and 2 root 3. Now we need to find the critical points. All right, so critical points. Critical points are where the derivative is equal to 0 or does not exist, okay, or undefined. So let's see here. We have the area function, 2x times 12 minus x squared. I don't want to do the product rule, so I'll just distribute. So we have the area as 24x minus 2x to the third. So if we differentiate this, we'll have a prime of x equals 24 minus 6x squared. Okay, applying the power rule to differentiate these two terms. So now we're going to set the derivative to 0 or find where it's undefined. So where is a prime equal to 0? So we're going to have 0 equals 24 minus 6x squared. Let's see what we can do here. If you add 6 to both sides, 6x squared equals 24. X squared equals 4. X equals plus or minus 2. Negative 2 is outside the domain, so we're only going to consider positive 2. So when is the derivative undefined? Where does it not exist? Since this function, we know what it is a parabola. It doesn't have any vertical tangents, cusp corners, discontinuities. It's smooth and continuous. So are we talking about this function right here? 24x squared. It's smooth and continuous, differentiable everywhere. So a prime is always defined. If you look at the derivative, it's a continuous function. It's defined for all real numbers, all real values of x. Okay, so when does it not exist? The answer is never. Okay, so we have only one critical point. So our potential extremas, we do not know if they are extremas yet, are 0, 2, and 2 root 3. Okay? Now we're going to shift gears and go to part 4, where we're going to classify these potential extremas. Okay, so classify. Alright, so we're going to start with the lower bound of our domain, a of 0. Remember, we are plugging this into the area function. A of x equals, let's see, what's the area function? 2x times 12 minus x squared. Okay, so a of 0 is going to be 2 times 0 times 12 minus 0 squared, which is 0. And then a of 2 is 2 times 2 times 12 minus 4. What do we have here? 4 times 8, which is 32. And then lastly, a of 2 rad 3, which is 2 times 2 rad 3 times 12 minus 2 rad 3 squared. 2 rad 3 squared is 4 times 3, which is 12, so this is 0. 4 root 3 times 0 yields 0. So we can clearly see that this is our maximum area. Alright? Okay, so now let's go back to our steps. Conclusion. What does this mean? Well, the problem asked for the dimensions of the rectangle for the maximum area. Okay, so let's state our conclusion. Part 5, conclusion. We said that the height is 12 minus x squared. So if x is 2, we're just going to plug in that x value into the function. So the height is going to be 12 minus 2 squared, which is 12 minus 4, and the answer is 8. Okay? And then the width is 2x. And then we know what x is. X is 2, so we have 2 times 2, which is equal to 4. Alright, so let's write down the dimensions. The dimensions are the dimension of the rectangle with a maximum area. Maximum area, we can even state what it is, of 32 square units is 8 by 4. Okay, so that's the dimensions, 8 by 4. Thanks so much for taking the time to watch this presentation. We really appreciate it. Feel free to subscribe to our channel for updates to other cool tutorials such as this. If you have any questions or comments, include it in the comment section below. More clips can be found on math.serve.com. Thanks again for watching and have a wonderful day.